Resolving power of telescope. To understand the resolving power of telescope, one must understand that the two stars which are being seen through the telescope, they are appearing distinct from each other, not merged into each other. And we have to obtain a formula for that resolving power. We should understand here the star which is far away is being seen through the telescope, and this lens actually represents the objective lens of the telescope. And we have to find only the resolving power of the objective lens. Every lens is a circular window called aperture. So this is lens aperture, whose diameter is equal to d. And the image produced by this lens of the distant star is not a sharp point obtained at the center, but is actually a diffraction pattern, which is comprising of bright and dark rings. So at the center, there is a bright ring, a bright spot surrounded by a dark ring and then surrounded by a bright ring. The graph of this one is clear here that shows the intensity is maximum at the center and it gradually fades down to produce a minima, which is in fact corresponding to a dark ring. See it from a different view. Now, in this case, it's clear that the central bright spot, which is in fact called airy disk, but many textbooks do not mention it. Airy disk has some radius and the surrounding dark ring has a radius represented by yellow line here. Now this yellow line, the radius of the first dark ring, often called R0, is subtending angle at the center aperture called theta. So I repeat, angle subtended by the radius of first dark ring at the aperture center, or just in short, aperture, is theta, which is given by 1.22 lambda, the wavelength of the monochromatic light, upon d, the diameter of the lens. Smaller the diameter, larger will be the diffraction pattern. Means if there are two stars, their diffraction patterns will be overlapping. And smaller the diameter, smaller, in this case, larger the diffraction pattern, larger the diameter, smaller the diffraction pattern. See here. This is how it happens. If you take bigger and bigger lens, the diffraction pattern shrinks and the angle theta becomes smaller. This angle theta is also called limit of resolution. Smaller the value of angle theta, that is 1.22 lambda by d, that is larger the diameter. In this case, smaller will be the diffraction pattern. It means a nearby star in this case will also be producing a diffraction pattern, but they won't merge into each other. So they will appear to be distinctly seen. We will see that soon, like in this case here. Now, in this case, there are two graphs which you can clearly see. One is red for the different star S2 and the other one is shown by blue color for the star S1. They are subtending some angle. Let's take the smaller, in this case, lens. Now in here it is showing us very clearly that the minima, that's first minima of the second star's diffraction pattern has enclosed, in this case, the center of the first star's image, or say diffraction pattern's principal maxima. When the center of the principal maxima of the first star lies inside the dark ring, then they are said to be not resolved. Here, if we say see the rough diagram, this is the image when they are not resolved. The resultant of the graph, that is after superposition of the two, blue and red, is shown by the white graph A single peak denotes that the stars are not resolved. But if you take larger lens or bigger and bigger lens, and then that reduces the size of the diffraction patterns, and a stage comes when the first minima, that dotted line, lies at the center of the first maxima of the other diffraction pattern, then the stars are just resolved. Still, there are two peaks. If we see white peak on white graph only, then for even larger lens, the peaks will be sharper, so they are getting better and better resolved. For smaller lens, the peak is single, they are not resolved. This is the condition when they are just resolved. So I repeat that. What should we write? We should say that the angle subtended by two stars here, this one, the larger angle between the red line and the blue line, let's call it phi. So phi is the angle subtended by the stars at the lens or the telescope. If phi is greater than theta, they are well resolved, and just equal to theta, they are just resolved. Theta is the angle subtended by the radius. So phi should be greater than or equal to 1.22 lambda by d for the stars to be resolved. The condition what you will write as phi is equal to 1.22 lambda by d will be the condition of the stars just resolved. So take the bigger lens, they are well resolved. Even if the stars are very subtending small angle, the bigger lens will solve the purpose because that will produce smaller diffraction patterns, keeping the first minima out of the center of the image of the first star. That's it.